Hi, my name is Stephen Webb. I'm a Senior Applications Engineer here at Parker Lord, and I'd like to talk to you about the presentation on a fast-curing structural polyurethane, and it's really focused on increasing manufacturing throughput. A little bit of an overview of the presentation. First of all, we're going to talk a little bit of background on the chemistry and the performance of urethanes and what was the impetus behind developing this new fourth generation. Talking a little bit about the urethanes and fourth generation performance, so what has led us to this new generation of the structural adhesives, as well as how it's significantly different than previous generations. And then finally, we'll talk a little bit about examples of increasing manufacturing throughput and some of the cost efficiencies associated with using a fourth generation polyurethane. So the impetus behind it, a need for a faster curing adhesive. Typically, the impetus has always been expressed by the customers when they say they've bonded their application, they've got their parts assembled, and the next question is almost invariably, when can I do my next operation? Be it cutting, moving the part down the line, moving it out of the tooling, painting it, cutting it, etc. Once the bonding operation is done, there's a desire to quickly move on to that next step. In typical application engineering, we've spent time ensuring that the customer's processes fit within the open time of the adhesive and then their handling times. So do we have enough time to lay out the adhesive for the size of the part or the complexity of it, and then go ahead and mate the parts together. Once that's done, you need sufficient strength in order to perform that next operation, be it painting, cutting, removing it from the tooling, etc. And typically in the past, acrylic adhesives, or MMAs, have excelled at this operation, that is, getting to the next step in the manufacturing due to their polymerization mechanism and the rate of reaction. So a little bit on MMAs or acrylics and how they have achieved the place that they do within manufacturing today and giving that high throughput. So this is a simplification of it, but basically the MMA synthesis process is one of free radical polymerization. That is, the monomer is mixed together with the catalyst, with the free radical is generated, and it's generally evenly dispersed throughout the adhesive. This allows the monomers to start forming dimers, trimers, etc., and growing the chains rapidly. And this has a direct effect on the macro performance. We'll talk about that a little bit in the next slide, or the next couple of slides. Polyurethanes, along with epoxies, are typically a slower rate of reaction and a slower process. The polyurethane synthesis is one of step growth polymerization. So again, we have one side of a monomer, typically a polyol, and the other side an isocyanate. Those, once they're evenly mixed, have to find a certain orientation on the molecular level. So enough on the chemistry, but basically it's the way it grows is slower. It has to find a certain orientation for the polymer chains to extend. So that direct effect. The MMAs typically, and this is why they've excelled in manufacturing, because you can do that next step in your manufacturing process quickly. So what we're seeing here is some typical cures of acrylic adhesives and the effect of free radical polymerization. On the left-hand side of the graph, you can see that percentage of cure. And so whether the adhesive has a 2-minute or 4-minute or 20-minute or 30-minute or even a 60-minute open time, those acrylic adhesives rapidly polymerize, and you can see the strength takes off in an exponential curve. And so very shortly after your open time expires, you've reached 60–80% of your ultimate strength, and then that's more than enough to move the operation to the next stage of manufacturing. Now looking at that slower step growth polymerization of traditional urethanes. So those urethanes, you can see the same thing. You've got those longer open times, 5 minutes, 10 minutes, up to 30 and even 60 minutes. But the curves tend to be more linear. And so it's a much slower rate at which they achieve that strength. And you can see that it's expressed in the curves. Typically, manufacturers have added heat to this process. And what it'll do is it'll shift the curve and give some additional strength, but it also adds cost to the process. So kind of getting that next step faster. A little bit of terminology first that adhesive manufacturers use. One of the first terms is open time or pot life or gel time. And so those refer to how long the customer has or you have in using the adhesive to lay out the adhesive after it's mixed and then mate the parts before the adhesive will no longer wet out the surface or develop sufficient strength in your part. And there's a lot of different terms. So pot life is an older term that goes back to mixed epoxy paints, the paint pot. And gel time really refers to an increase or a doubling of viscosity. All of these are kind of nebulous, and they allow manufacturers to kind of give an indication to the operator, but it typically takes an application engineer to kind of dial in the process. The next term is really kind of handling time or fixturing time, or what the time is for that part to sit and rest till it reaches kind of a very minimum strength to be moved aside. And so that's typically that handling time or fixturing time, and depending on the manufacturer, it'll either be 50 or 100 psi. Now, the term that I want to introduce is really processing time. Processing time is the amount of time of cure needed for an adhesive or joint to develop sufficient strength to withstand that next manufacturing step, be it either cutting or painting or dimensional tolerancing or removing it out of the fixture, rough handling, etc. Nominally, a good rule of thumb would be about 1,000 psi or 6.9 megapascals. So we can see here on this slide, talking about the processing strength in the 4th generation polyurethanes that Parker Lord has introduced. Graph on the right shows the strength development, and this has been measured via ASTM D1002, lap shear strength, on E-coated steel. You can see here that the 2nd generation urethane, 3rd generation, 4th generation are all represented, and all of them have a 3 to 7 minute open time. So with the 2nd generation in gray line, it takes, even though there's 3 to 7 minutes of open time, it takes 9 to 10 hours to reach that strength of 1,000 psi, or the processing strength that we've indicated on the previous slide. 3rd generation polyurethane, again, 3 to 7 minutes of open time, takes between 2.5 and 3 hours. And the newest generation of adhesive, structural polyurethane, a 4th generation, takes only 1 hour to generate that processing strength of 1,000 psi. Now I'd like to talk about a little bit about that processing time on the 4th generation polyurethane and how it relates to the MMAs. So again, as we talked earlier in the presentation, the MMAs, or acrylic adhesives, are really the ones that have driven the rate of manufacturing by their strength development and how fast we can get to that next stage in the manufacturing process without adding heat, and again, adding cost in the manufacturing process and tooling. You can see here that those 2nd generation and 3rd generation structural polyurethanes take between 9 and 10 hours and 2.5 hours on that processing strength column, whereas the 4th generation structural urethane by Parker Lord is that Lord 7800, takes only 1 hour. And in comparison, the Lord MMA takes also 1 hour. Again, a 3 to 4 minute open time acrylic adhesive. The cure here was done at 21 degrees Celsius, and you can also certainly add heat to any of these adhesives and accelerate them. With the new 4th generation structural urethane, you can actually get down to as little as 90 seconds. One of the concerns with using fast curing urethane is they typically generate quite a bit of heat, or exotherm, during the curing process. So acrylic adhesives, or MMAs, some of the earlier generations certainly are notorious for generating so much heat that when used on composites such as FRP or thermoplastics, that they can actually begin to melt and deform the finished part, leading to visible bond lines through the part. So this is a concern with manufacturing. It's often called read-through or print-through. The 4th generation urethane, although it is a very fast urethane, has roughly the same peak exotherm of 60 to 70 Celsius, in that range, as the previous generation 2nd and 3rd. So there's no real concern here where the heat is generated is not necessarily correlative to a faster cure. Lap shear performance. So this just shows some general performance on a variety of materials of this newest 4th generation structural polyurethane from Parker Lord. We've measured the shear strength via the typical methods of ASTM D1002, 3163, and 3165, depending on the material used. Although that the strengths in the center are much lower, it should note that we saw stock failure, fiber tear, or coating failure, some of the best performance achievable by an adhesive on all the different materials. So the thermoplastics such as PMMA, ABS, polycarbonate, acrylic polycarbonate ABS blend all broke during the lap shear testing. The carbon fiber, CFRP, generated much higher strength and had fiber tear, and the E-coated steel actually deformed the steel and pulled the coating, the E-coat, off the steel. So now I'd like to talk a little bit about using these 4th generation polyurethanes to reduce cycle time in manufacturing. First example I'd like to cover is really within the heavy-duty truck community, where they're building heavy-duty truck hoods either out of FRP or meton-type products. In this example, the customer was using SMC and FRP. They used heated tooling and a competitive 2-component heat-cured polyurethane to achieve their strength. One of the concerns, however, they had was with the FRP, the gel coat on the surface was subject to degradation due to heat. So there was a slower process associated with the FRP and a lower temperature. So looking at this one, we used the competitive adhesive, we used the Parker Lord 7800. What we were able to achieve is taking about 2 minutes out of the manufacturing time for the SMC with heated tooling, and we also lowered the strength by 70 degrees Celsius. This is particularly advantageous if you have startup in the morning or cool tooling or cold spots in the tooling, and you're unable to achieve that with traditional or competitive two-component heat-cured polyurethanes. They will not cure, and so you have quality issues typically when there's lower strength involved. With the FRP, as I mentioned, there's a longer cycle time and a lower temperature. Although we weren't able to lower the temperature on this one, we did also remove 2 minutes from the manufacturing process. I'd like to talk a little bit about lightweighting trends, particularly coming from Europe, where they started this earlier, lightweighting of automotive and heavy-duty truck components, but certainly lightweighting of all components. This is for fuel efficiency. In this particular example, I'd like to talk about the liftgate in automotive. In the past, this has traditionally been a steel or SMC outer shell. That's the Class A surface that's painted. And then the interior members that are the reinforcing members have typically been out of some sort of FRP or SMC. As they're moving now towards these lightweighting trends, the materials are changing, and those inner reinforcing members tend to be glass-filled thermoplastics. So again, with the lightweighting trend, we want to talk a little bit about performance of this fourth generation polyurethane on some of the newer materials. One of the materials that's being used is a 40 or 30% long glass fiber filled polypropylene. Again, a low surface energy material does require surface treatment to achieve that. But typically, what's used in bonding these substrates together are low modulus polyurethanes. One component material, moisture cure, one component MS polymers that are moisture cure. And oftentimes they can't achieve their cycle time because of the rate of reaction that uses moisture to cure it. Typically, manufacturers then increase the viscosity and make it a much more of a viscous paste to sort of hold the parts together so they can gently be removed from the tooling. Oftentimes, however, there are quality associated with this. What I wanted to highlight here is the performance on the new 7800 fourth generation polyurethane on these long glass fiber polypropylene substrates. The first one, where we did just an alcohol wipe, that's a very low surface energy. It's only about 32 dynes, and you can see, as expected, adhesive failure, fairly low strength. But either with a flame treatment or a flame treatment where we did a simulated paint bake cycle of 30 minutes at 250 Fahrenheit or 121 Celsius, a flame treatment only or a plasma treatment only, you can see we achieved stock break in all cases. One of the next case examples I'd like to talk about is automotive headlamps. Headlamp manufacturers have typically moved over in recent years to one component reactive hot melts, or PURs, for bonding the headlamp assemblies together. One of the issues, however, with this manufacturing process and with this tier of the automotive segment is that the tiers have to perform a 100% check on all the units to prevent leaks, which requires building a time queue in prior to this pressure check, typically 1 to 2 psi. And this usually leads to about 30 or 60 minutes delay in the manufacturing process. With this example, I'd like to highlight, in this case, just a circular headlamp where we did testing on it. We did the traditional pressure check of between 1 and 2 psi. Some manufacturers use 1.5. In the first example, we did a room temperature cure. This product has a 4 to 7 minute open time, the 7800 AD, and we're able to achieve those positive pressure checks in as little as 18 minutes. Interestingly enough, when we add an IR lamp to it, we can dramatically decrease the cycle time before that pressure check. In this case, we were able to achieve about 5 minutes before we did the 1 to 2 psi check. I should note also that the Lord 7800 AD is the fourth generation structural polyurethane, has been qualified to the General Motors worldwide standard 16506 for automotive lighting. One other additional feature of the Lord 7800 is that we've added a UV trace material into the formulation. This allows for quality checks relative to machine vision. The example here you can see is a second generation black polyurethane on a black hair cell ABS. And then on the left-hand side, we have the 7800 fourth generation. On the right-hand side picture, when you can see it's exposed to UV light, the material fluoresces, generating a relatively easy product to see for a rapid visual check of where the adhesive is laid, and also allowing for machine vision to check for 100% coverage. I'd like to talk a little bit about the composite heated response of the fourth generation structural polyurethane. In this table, what we've done is we've generated the strengths on how quickly it develops strength. And manufacturers have typically, once they've used a polyurethane in their manufacturing process, may have heated tooling already in place. I'd like to show the response of this fourth generation. In this case, we used lap shear response on 3mm thick polyester SMC and a two-sided heated tooling. The lap shear strength was measured after that particular time in the tooling, as shown by the column on the right-hand side, 1 minute, 2 minutes, 3 minutes, etc., all the way up to 10, and then a 2-minute dwell time prior to testing. This was then compared to the ultimate strength on the SMC after 24 hours of room temperature curing. What we can see here is that the various temperatures, 82 Celsius up to about 116 Celsius, or 180 Fahrenheit to 240 Fahrenheit, we can rapidly develop greater than 2/3 of the strength of the ultimate yield of the product for this SMC within a short amount of time just by using this heated tooling. So overall, the fourth generation structural polyurethane has a good response to heated tooling, and it's really a low heated tooling. Again, this goes back to the fact that sometimes tooling isn't sufficiently heated at the beginning of production, or there may be cool spots in the heating and the tooling itself leading to quality problems. In this case, the fourth generation polyurethane is a room temperature curing. So if the tooling doesn't achieve sufficient heat in one area, the product will still cure and we won't have a quality issue with the part. However, as you can see here, you can lower the tooling temperature and typically extend the life of it.